Good afternoon. My presentation is on the Buildings chapter of IPCC 6 Assessment Report, Work Group 3, Introduction for Buildings and Mitigation Technological Options and Strategies Towards Zero Carbon Buildings, Chapter 9.4. And my name is Görkem Güngör. In 2019, the greenhouse gas emissions from building sector amounted to 12 gigaton carbon dioxide equivalent, which is 21% of global greenhouse gas emissions. The on-site emissions were 57%, while off-site emissions were 24%, originating from electricity and heat, and the remaining from construction materials production and refurbishment of buildings, which amounted to 18% from all greenhouse gas emissions. The residential emissions covers 50%, while non-residential amounts to 32%, and embodied emissions amounts to 18%, which is in total 31% of global carbon dioxide emissions. The final energy consumption of the building sector was 128.8 exajoule, where 43 exajoule is for final electricity, which amounts to 33% of total final energy and 18% of global electricity demand. When we look from 2005 to 2020, there has been a reduction of final energy demand in the buildings sector from 2005 to 2010. However, after 2010, the trend reversed and the final energy demand started to increase. This means that the energy efficiency gains has come to the limit, and starting from 2010, we have increasing final energy demand from the building sector. The sufficiency, efficiency, renewables framework is mentioned in this report section. This is mainly a Eurocentric approach where the European Union takes the lead in energy transition to achieve the net zero target in 2050. From the Sankey diagram, we can see that imports has diminished in 2050. The fossil primary energy input has also diminished. We have an increasing electricity demand for secondary electricity, increasing from 3.3 exajoule to 6 exajoule in 2050. We have addition of hydrogen for sectors including industry, transport, and residential sectors. And as thermoelectric generators have diminished, we have reduced the losses from 3.8 exajoules for final energy demand to 1.3 exajoules. The assumptions of this framework is based on, for the building sector, fairness in living space per capita and passenger transport demand, which are two main pillars of the urban energy system. And this depends on the transition speed and sets minimum and maximum levels so that this fairness can be achieved. There are cross-sectoral linkages with industry, transport, and food sectors. Biomass is crucial as the human urban environment is also dependent on agroecology practices, which also provide bioenergy supply. However, the scenario requires high grid resilience against external events. We have less flexibility, requiring higher resilience for grid stability. The mitigation technological options, the digital and green transition, mentioned as twin transition, is one of the main enablers for mitigation in the building sector. The effect is on clean distribution energy grids. The digital and green transition supports the transition of the energy grids to smart and clean systems. Smart urban mobility, where the mobility energy demand can be coupled with building sector energy demand. The precision agriculture, where the water stress can be reduced, the crop efficiency can be enhanced to supply food and also bioenergy demand. The sustainable supply chain, where we have reuse, recycle efforts. Environmental monitoring for both supply forecast and also demand prediction, and enhanced weather prediction, especially for mass penetration of renewable energy. And the twin transition is supported by the information and communication technologies, which have been expanding since the last decade with more mobile and broadband communication channels, sensors, databases, big data collection, and analysis of this big data using digital technologies such as the artificial intelligence and machine learning algorithms. All these favor the smart and efficient energy usage in the buildings sector and the urban environment, which includes also industry, agriculture, and transport sectors. There is a big potential in information and communication technologies. Nearly 6 billion people have online access to internet in 2025, and there is additional 2.2 billion people which have to be introduced to this online access. There is a regional disparity in internet use. The world average is 74%. We have the highest in the former Soviet republics and Europe, exceeding 90%. In the Americas, this is 88%. In Asia, Pacific, and Arab states, this is 70% and above. In Africa, we have 36%, which is also shows a big potential for further usage of internet. There is a divide between urban and rural use. As urbanization is enhanced, more people will have access to information and communication technologies. We can see that in Africa, 55% in urban regions have access to internet, whereas for rural regions, this is 21%. And urbanization is one of the main enablers for enhancing information and communication technologies. There are strategies towards zero carbon buildings and also nearly zero emission buildings. The Internet of Things with appliances, digital communication, and data transmission through sensors. These have been evolving to the Internet of Energy with a smart network of industrial energy producers and consumers, which can establish microgrids, including demand centers such as houses, factories, hotels, and both suppliers and demands of energy, such as villages and farms, electric cars, commercial buildings, and the Internet of Energy provides digital infrastructure to establish these kind of microgrids. In fact, these microgrids require small generators. In the initial phase of the electrification era, there were actually small producers. With the scale of economy, they converged to big producers. Now we will have a reverse to again small producers, but with digital technologies. The specificities of Internet of Things is their scalability, the measurement precision, unique identification of producers and suppliers, dynamic adaptation to turbulences, and self-tuning, matching, and diagnostic capabilities, which enhance the resilience of microgrids. The article mentions about case studies in utilities such as Duke Energy, GE, and Schneider, and some microgrid applications such as in the New York City, in the USA, and in Canada. These are mainly in developed countries, but as these case applications increase in the world, in the developing countries, we expect a wider application of digital and green technologies. There are challenges to the twin transition. As there is big data, their confidentiality and integrity must be established. The identification of the producers and consumers must be clearly defined. There might be tampering of data, trust issues, and privacy concerns, which are all related to personal data, and access control and authorization. These are also crucial for the exchanges inside the microgrids. And in the end, we have the human in the center, which requires social adaptation to this transition and higher management capabilities. As there is more decentralization, there is more distribution of management, and there has to be trust relationship, and these challenges have to be mitigated together with the increasing management capabilities. Thank you very much for your kind attention.